Okay, welcome everybody to the Astrostatistics and Astroinformatics seminar series, which is sponsored by the International Astronomical Union and International Astrostatistic Association. We are very pleased today to have Professor Jason McEwen as a speaker. Before we start, a few technical info. Due to the usually high number of participants, we prefer to keep all the microphones muted. We recommend to keep the questions for the end of the seminar. The standard procedure is that you raise your hand and I'm gonna unmute your microphone. Anyway, in case you have a very urgent question during the talk, you can write in the chat and I'm gonna allow you to intervene and directly ask the question to the speaker. Thank you for your understanding. So today the speaker is Professor Jason McEwen. Jason is a professor of astrostatistics at the Molar Space Science Laboratory at the University College in London. He completed his PhD at the University of Cambridge and since held a junior research fellowship at Clare College, always in Cambridge, followed by a Langevin Early Career Fellowship and a Royal Society Newton Fellowship at the UCL, before taking up a faculty position. He is also the founding director of research of the UCL Data Intensive Science and Industry Center and has been involved in numerous astrophysical experiments, including Planck, Euclid, Rubin LSST, and the SKA. He is also the founder of Kaginova, a startup company specializing in geometric deep learning for the metaverse and beyond. Jason has broad multidisciplinary research interests that include the Bayesian inference, uncertainty quantification, computational harmonic analysis, machine learning, and geometric deep learning. Among his recent working projects, there is Bayesian model selection for likelihood-based inference and simulation-based inference, which is the subject of today's seminar. So Jason, the stage is yours. You can start when you want.
Thanks very much, Fabio. And yeah, thank you very much for the invitation to talk to you all here today. As mentioned, I'm going to be speaking about Bayesian model selection, which I think is probably a topic familiar to most of you on the call here. So I'm going to motivate it and give it a background, but I'm going to go through that super fast, but really just to set the notation, set the scene for what will follow. And then I'll be talking about a number of recent works, new techniques for likelihood-based model selection to compute the Bayesian evidence or the marginal likelihoods, how these techniques can be applied and extended to a simulation-based inference setting, and then also how we can try and scale Bayesian model comparison up to high-dimensional settings with new proximal nested sampling type approaches. So firstly, just to set the scene super quickly, as we all know, we have one universe to observe. We can look back and observe the galaxy distribution. We could look back further to the epoch of reionization or back further still to the CMB. And in all of these epochs, I'd say there are still many fundamental unanswered questions that we're trying to address. From observations of the CMB, we can learn about the origin of structure in our universe, but there are a lot of inflationary models to be considered. The epoch of reionization, we want to understand how ionized bubbles form during this epoch and how to model these physically and what are the dominant sources. In the more recent evolution of the universe, we can learn a lot from large-scale structure in particular to try and constrain the nature of dark energy. These are very much kind of questions of cosmology, but on the more astrophysics perspective, as I'm sure everyone's aware, we've recently detected gravitational waves. And again, now we want to use these observational signals to understand the physical processes responsible for various astrophysical phenomena, such as merging black holes. So all of these questions are really questions of model selection. Yes, we do want to constrain the parameters of these models, but fundamentally, to answer these kind of fundamental questions about the physical nature of our universe, we want to address this question of what is the appropriate model. And in cosmology, we don't have the luxury of being able to perform experiments. We just have one universe to observe. In astrophysics, so for example, gravitational wave type observations, again, we cannot perform experiments. We may have a small number of observations instead of just one, but nevertheless, the number of observations is highly constrained. And so this has really given rise to the prevalence of Bayesian model selection in cosmology in particular, and also in astrophysics. So I'm going to just recap Bayesian model selection super quickly, really just to set the notation, and then focus on three main topics. New estimators for likelihood-based model selection, for simulation-based model selection, and then for really trying to push to high-dimensional settings. So a very super quick recap. I'm sure everyone on this call is very familiar with Bayes' theorem, where we relate the posterior to the likelihood and the prior and the evidence. Really, I just want to set the notation. I'm going to use this mathcal L, the calligraphic L for the likelihood, pi for the prior, and Z for the evidence unless otherwise stated. And so to do parameter estimation, typically we'll try and sample from the posterior through MCMC sampling. But we don't only want to constrain the parameters of our models, we want to try and ascertain what is the correct model. So we can apply Bayes' theorem again to the probability of the model given the data. And for model selection, we really want to compare the posterior odds, the model posterior odds. And this is related to the Bayes factors and the prior odds simply by applying Bayes' theorem on the left there. So we need to compute these critical factors called the Bayes factors, which involves computing what's called the Bayesian model evidence, also called the marginal likelihood, which is basically this normalizing constant that appeared in Bayes' theorem on the previous slide. So this is a multi-dimensional integral of the likelihood and the prior. And in high-dimensional settings, this can be a really challenging computational problem. So this is really the crux of the matter. How do we compute this model evidence or marginal likelihood? The model evidence naturally incorporates Occam's razor. This is a diagram, I think, first introduced by David Mackay, where we have all possible data sets on the x-axis. And if we have a complex model that can represent lots of different types of data sets, it's going to spread its probability across those data sets. And so it's not going to do so well to represent simpler models. So in this sense, the evidence naturally trades off this Occam's razor to trade off complexity versus goodness of fit. I'll just comment very briefly on priors. I mean, this is sometimes an issue of contention in the Bayesian framework. There are actually a lot of different ways you can go about trying to select your priors. In some cases, maybe they can be informed by the physics of the problem. For example, constraining mass to be positive. Sometimes you might want uninformative priors where you encode invariance to symmetry transformations, or maybe actually you do want informative priors. For example, if you're trying to regularize inverse problems. You can also consider the setting where your prior is actually informed by data. So maybe old data, there's a previous experiment that basically defines your prior knowledge. Then you want to consider how to update that prior knowledge in the context of new data. And then also finally, you can have data-driven type priors where you try and estimate the prior from the data or even from generative models that learn from a lot of training examples, for example. So there's a lot of different ways you can go about this prior selection issue. I'm not really going to talk about that anymore, but for now, I'm going to assume we've got some appropriate priors for our problem at hand. So we want to compute this Bayesian evidence. We can just do this by a naive Monte Carlo integration of the marginal likelihoods. However, this estimator is a very large variance, and that is really again, the crux of these kind of methods, how we can have estimators that have a reasonable variance, because in this case, the naive Monte Carlo integration approach just becomes ineffective, really even in still relatively low dimensional settings. So we need techniques tailored specifically to the computation of the marginal likelihood, not just picking up standard Monte Carlo integration approaches. And I'm sure people are very familiar with a lot of existing techniques in this area. There's been a lot of progress, and Bayesian model selection is now quite well integrated in astrophysics and cosmology. People are probably very familiar with nested sampling, and multi-nest, and polychord, and dynasty, and a lot of these codes, which have been very prevalent. So I'd say, there's been a huge amount of progress made. However, there are still a number of outstanding challenges. Nested sampling can be very effective. And actually, I'll come back to this later in new nested sampling techniques to scale to high dimensional settings, but it nevertheless does impose constraints on how you sample. So actually, in some cases, you might want much more flexible approaches that can then open up alternative types of application. So in the remainder of the talk, I'm going to focus on basically recent work we've done in these three areas: more general flexible sampling approaches, how to extend these approaches to the simulation-based inference setting, and then proximal nested sampling techniques to scale to high dimensions. And how are we going to address these problems? Essentially, we're going to try and leverage ideas from different types of paradigms. Of course, we're in a statistical framework, Bayesian framework, but we're also going to leverage ideas from essentially machine learning, from computer science, also developing professional software codes. So we want to bring to bear machine learning to these problems, but also some ideas from applied math, and in particular, proximal calculus and optimization approaches. And all of these different paradigms have different pros and cons. And if we can leverage them together, we can hope to try and realize all their different strengths at the same time. So that's the kind of general underlying focus of these techniques that I'm going to speak about. So the first one, we're going to look at integrating machine learning into some statistical estimators. And that's led us to what we've called the learnt harmonic mean estimator. Let's first consider it in the context of likelihood-based model selection. So the learned harmonic mean estimator has been around for a long time. It was first proposed by Newton and Raftery in 1994. And it's essentially, well, as the name suggests, the harmonic mean of the likelihood. So if you consider the expected value with respect to the posterior of the reciprocal of the likelihood, you can expand this out, express this as an integral with respect to the posterior. If you substitute in the posterior now in terms of the likelihood, the prior, and the evidence, the likelihoods cancel. The prior is a normalized probability distribution that integrates to 1. And so this expression just gives you 1 over the evidence, or 1 over the marginal likelihood. So this suggests an estimator to estimate the reciprocal of the evidence, which is simply the sum of 1 over the likelihood given posterior samples. However, it was realized almost immediately that this estimator can fail catastrophically. And in fact, it's been famously called, I think, the worst MCMC estimator ever. So what we're going to do is try and look into this estimator a bit more, get a bit of intuition into why it fails catastrophically and how we can mitigate this failure. So there's an alternative way of viewing the harmonic mean relationship that we just considered previously, and that's as follows here. You can write it as this expression that's highlighted, and you can see that this is really important sampling, but it's important sampling where the target distribution is the prior, pi, and the sampling density is the posterior. And actually, this is the reverse of the usual important sampling setting. Usually for important sampling, we want the sampling density to have fatter tails than the distribution we're targeting. But that is not the case here. The distribution we're targeting is the prior, which is typically fatter than the posterior. So in some sense, it's not a surprise, actually, that the standard harmonic mean estimator can fail catastrophically. We're essentially doing important sampling, but in the setting where important sampling doesn't work well. So to get around this issue, it's possible to introduce an alternative important sampling target, phi here. So this was suggested, again, at much the same time by Gelfand and Day in 94, where we introduced this phi distribution, which critically must be a normalized probability distribution. And then if we simply expand this, express this in terms of the integral with respect to the posterior, substitute in the posterior, the likelihood and the priors now cancel. We get the integral of this introduced important sampling target phi, which integrates to 1, and we get 1 over the evidence. So this suggests the following estimator, where again, we take samples from the posterior and we form this estimator here using this important sampling target var phi, which we have the freedom to choose. So again, we can consider the same important sampling interpretation, and really now we've just replaced the prior with this introduced phi distribution. And since we're free to choose this, we can ensure that it doesn't have fatter tails in posterior, so that we're in a situation where important sampling works well. So we know conceptually some of the constraints on this target distribution phi, but the question still remains, how do we set this in practice? And a number of cases have been considered. Multivariate Gaussian has been considered. The problem with this is typically the Gaussian is too broad, and you end up still having probability mass in regions where the posterior might be very small, which gives rise to this catastrophic failure. Another suggestion is using indicator functions. The problem with this approach is that, especially if you have complex posterior distributions, these indicator functions can end up only capturing a very small region of the parameter space, and these methods can be inefficient. So what we can do is get some intuition on what would be the optimal target, what would we ideally like to do. And it turns out that the optimal target is simply the normalized posterior itself. You can quite easily show that for this target distribution, the resulting harmonic mean estimator has zero variance. However, the problem is that using this distribution, we would have to have solved the problem already. Remember, this distribution phi needs to be normalized. And so we need to have a normalized posterior, and that's in fact the problem we're trying to solve. So unfortunately, we can't do that, but we can nevertheless get intuition that, that would be what we'd ideally like to do. Maybe there's some way we can approximate this optimal distribution. So that led us to develop what we've called the learned harmonic mean estimator, where we learned here basically represents, we're integrating kind of machine learning to learn an appropriate phi distribution. So this is work done with a number of postdocs and PhD students at UCL, Chris Wallace, Matt Price, and Matthew Doherty. So what we do with the learned harmonic mean estimator is essentially use machine learning to approximate this optimal, the normalized posterior distribution. And critically, this approximation actually doesn't even need to be very good. It doesn't matter if we don't necessarily approximate the posterior very well, but what is in fact critical is that we must not have fatter tails than the posterior because of this important sampling distribution. So this gives us some ideas for how to go about learning appropriate machine learning models that, remember, critically normalized. So they don't need to be a good approximation necessarily of the posterior, but critically they must have narrower support than the posterior. So we basically develop a strategy to estimate, to learn this distribution, or appropriate models of this distribution, and then also estimate not only the harmonic mean estimator itself, but also the variance of the estimator, its variance, and other sanity checks. So we consider, just very briefly, without getting into too many details, the way we learn this target distribution is we consider a variety of machine learning approaches, but critically, we train these models in a different way. We don't just train them in the traditional manner, we train them for the problem at hand. So we specifically train the models to minimize the variance of our resulting estimator, also while ensuring that they're unbiased, and in some cases, we also introduce regularization. So we set up specific optimization problems that we solve for this problem to give us a learned harmonic mean estimator. And then we essentially solve by a mini batch stochastic gradient descent and use cross-validation to set hyperparameters. So that's the learned harmonic mean estimator in a nutshell. I've kind of glossed over some of the details, but you can see the paper if you're interested in learning more. Let me just show you some examples on a few toy problems. The standard Rosenbrock problem, where now we have this pronounced curving degeneracy. We can sample with, in fact, any MCMC sampling approach. That's a great advantage of this harmonic mean estimator, is that all we need is posterior samples. We're completely agnostic to how those samples are captured. So we sample using the EMC code, and then we compute our harmonic mean estimator. And in fact, we run this multiple times. So the measured violin plot here shows, I think, the result of 100 trials of this experiment. The blue shaded area shows the distribution of the estimator. The purple shows the mean and one standard deviation from all those trials. On the right, we show, as I mentioned before, we not only have an estimate of the evidence itself, but also its variance. And so the green error bar is what we computed just for one trial. We can compute an estimate of what we think the uncertainty should be, and you'll see that indeed it's very accurate. Again, we also even look at the variance of the variance, and again, we have an estimator for that and a number of other sanity checks. We consider another example, in fact, a common benchmark from papers that have looked at Bayesian model comparison, and was shown in this review paper that this was a pathological failure of the harmonic mean estimator, where the harmonic mean estimator fails catastrophically. I'm not really going to go into much detail on what the model is. It's a fairly simple model. We can simulate data for this model. But the nice thing about it is we have an analytic expression for the evidence. Again, I'm not really going to go into details. The only critical point to note is that an analytic evidence exists. So we can compare to a ground truth computed using the analytic evidence. So here we show now results for a number of priors. So the x-axis is as the size of the prior changes, and what we're plotting is the ratio of the estimated evidence to the analytic evidence. So if things were correct, this would be 1, so the red line is the ground truth, and we can see our estimators are generally accurate and the error bars are appropriate. But critically, we are indeed sensitive to the prior, to changes in the prior, which this previous review paper found with the standard, the original harmonic mean, was not the case. So this just shows the values themselves. And basically we get, so our error is very small, on the order of 10 to the minus 4 here. So we have about 4 orders of magnitude improvement in accuracy compared to the original estimator, which was completely ineffective on this problem. I've got another problem here again.
Jason,
sorry.
There is a question from Tom Lorido that asks, what are the dimensions of this test problem?
They're relatively small, this one. Yeah, I can't remember what we ran off the top of my head. I'll have to check the paper. But these are relatively small toy problems. I think, yeah, I'll need to check, sorry. Anyway, I can look quickly, maybe in the questions.
Okay.
Unless there was a follow-up question related to that. Or...
No, I don't think so.
Yeah, so all of these models I'm showing now are very much toy models, but they're actually models that have been considered quite a lot in these in a number of, they've become kind of common benchmarks for evidence estimation techniques. There's this radiated pine one where we're using a standard data set. The question is basically, is density or resonant adjusted density, which is the better predictor of compression strength of these radiated pine trees? Again, I'm going to kind of skip the details of the model. It's a relatively simple hierarchical model. Again, the critical thing is the analytic evidence can be written down and calculated. So we've got a ground truth to compare to. And again, we get very good accuracy and much better accuracy than the original harmonic mean estimator, essentially because we've ensured our learned target is a relatively good approximation of the posterior, which basically means we're efficient. We can use as many samples as possible, but at the same time, critically, the tails are within the posterior. So we don't get these large samples that contribute a very large variance to the estimator. We've released open source code that implements this estimator, which we call Harmonic. We put quite a lot of time into trying to make sure it was well designed and easy to use. It's well documented, well tested, and really, as I mentioned, we're agnostic to the sampling method, so you can use it with whatever method you have to generate posterior samples. We've typically used it with the EMC MC sampler, and in fact, there it's we've really tried to make it very easy to use with the sampler and also others that have similar interface. So it's really nothing more than just a few lines of code to basically train the harmonic target model and then apply it to compute your evidence. So if you've got posterior samples to hand, you don't need to necessarily redo any sampling. You can just apply this harmonic approach and now get evidence as well. So that's all I wanted to say about the harmonic mean estimator in the likelihood-based setting, let's now turn our attention to simulation-based inference. So I'm going to just recap. I mean, again, maybe many people on the call are familiar with simulation-based inference, but I'm going to just do a very brief recap just to kind of set the notation and the concepts that we'll then build on top of. So in simulation-based inference, we consider the setting where the likelihood may simply not be known or may be intractable. So there we essentially seek to perform parameter inference by estimating the posterior from observational data and then using simulations only. So that's the key thing. This is sometimes called likelihood-free inference, but more recently the name simulation-based inference is stuck because in settings, maybe there is a likelihood, or at least a surrogate likelihood that you're learning. So it's not necessarily always likelihood-free, but the key point is that you're really trying to address this inference problem through simulations only. So the advantage of that is we can have very complex simulations. We can forward model, the complex physics of a process, any foreground contamination, for example, or other contamination, the observational process involved in systematics. So we can have very extensive forward models that can capture a lot more detail than simple kind of parametric models of these processes. And also, we don't need to make any assumptions now on the form of the likelihood. So there are a number of approaches to simulation-based inference. There's also an approach called approximate Bayesian computation, ABC, which you might have heard of. I'm not really going to cover that any further today. There have been a number of developments more recently in an approach called neural density estimation. And these are the kind of techniques that I'm going to talk about further today. So there's essentially three flavors of neural density estimation, where one, you try and learn the posterior itself. So in PE, neural posterior estimation, or you try and learn the likelihood. So you try and learn a surrogate likelihood. In LE, or you try and learn some kind of ratio related to the likelihood. It's essentially the likelihood to evidence ratio. So most of the attention to date for neural density estimation approaches has really focused on parameter estimation. How do we estimate parameters in these settings? And in fact, neural likelihood estimation in particular has found a lot of application in cosmology already, and a lot of interesting studies in that space, for example, by Ben Van Delt and Justin Elsing and others. But a lot of the attention to date has been focused on parameter estimation. So we want to see how can we do model selection in these settings. So yeah, just to very briefly recap these three methods, I'm really not going to go into any detail in the interest of time, but essentially just to say, typically we'll have training data where we have parameters drawn from some, let's call it a proposal prior, maybe the underlying prior, but it may not be. And then we also are going to consider simulations of our data. So that's the key thing. We need a simulator. And then in PE, we essentially learn an approximation or a surrogate of the posterior. It's developed first by Papamacarius and McKay, but a number of following interesting articles built on this as well. Oops. Within LE, we now try and learn the likelihoods. And then within RE, we learn a density ratio, which is in fact the likelihood to evidence ratio. And the key thing with this approach, actually, you can train it in a quite different manner, where you actually just need to train a binary classifier to discriminate samples drawn from joint and marginal distributions. So I'm not really going to get into how you train these models, or there's a lot of interesting work on this topic, and I've cited a few of these key papers here. But what we want to address now is how we're going to do model selection in this setting. Oh, I forgot to say one final point is that you can amortized or sequential approaches for simulation-based inference. So in an amortized setting, you basically train some density estimator such that it can then run multiple times for different types of observations. So you don't specify just a particular data instance. A sequential approach, on the other hand, you do usually specifies to a particular observation, typically train and runs, and actually this can end up being a lot more efficient. So we're going to consider both these amortized and sequential approaches. So this is work that we published, well, we submitted recently. It's still under review, but it's on the archive, and it's work with Alessio Spirio-Manzini, Matthew Doherty, and Matt Price, who are all postdocs or PhD students working with me at UCL. So before we get into our techniques, let's also consider a naive approach that one might, maybe the first thing that might come to mind when you think about trying to do model selection for SBI. So we know with NPE, neural posterior estimation, we can learn a posterior. With NLE, we can learn a likelihood. So what we could do is simply take the ratio of these two things and essentially back out an evidence. And so you could consider an estimator as written here, where you also have to account for the prior. But every sample now gives you an estimate of the evidence, and you can just combine as many samples as you have. So we did actually try this approach as well. It's been mentioned, I think, a couple of times in the literature. I've never actually seen anyone apply it. We actually found that this the variance of this estimator was very large. And I think that's essentially because you're taking the ratio now of two approximate quantities. And as soon as you have errors in both of these, then these errors compound. And we found that the accuracy of this estimator is relatively poor. So instead, we consider alternative approaches to compute the evidence in these SBI settings, where we essentially make use of the harmonic estimator. So we have an approach for both, well, for all the NPE, NLE, and NRE settings. So let me just briefly go through each of those. So for the neural posterior estimation approach, we train an NPE model, but we also train an NLE model. We use the surrogate posterior to draw samples directly. So with NPE, you can usually avoid MCMC sampling and just draw samples directly from your surrogate posterior, which can be highly efficient and often can be computed in parallel as well. So that gives us samples, and then we just essentially use the NLE model to evaluate an approximate likelihood at those samples, and then we use the harmonic mean estimator, well, the learned harmonic mean estimator as written here. This kind of approach, although we're evaluating the likelihood, we're not doing MCMC sampling. We have, we just have samples essentially given to us. So this is where the flexibility of the learned harmonic mean estimator is critical. We need something that's agnostic to how we've collected samples. All we need with the harmonic mean estimator is samples from the posterior. So it's the harmonic mean that allows us approach that allows us to address the problem in this manner. Because we remember learn this phi distribution, but as I said, critically, we're not really sensitive to the accuracy of that. So we avoid the case that we had previously where we had ratios of things where we were very sensitive to errors. So we avoid this kind of compounding error situation. And one could even consider this in a likelihood-based setting, simply as a way to accelerate evidence calculation as well, where you could avoid MCMC sampling. So that's the approach for NPE. For NLE, well, we've got a surrogate for the likelihood. We can then just do MCMC sampling, and we can then just make use of that surrogate likelihood in our harmonic mean estimator. So it's fairly straightforward. With this approach, we do need to do MCMC sampling, so that can be slow. We also avoid any compounding errors, but we also only need one model. We just need the likelihood. And then finally, we can also consider this neural ratio estimation setting, where again, typically with NRE, you would perform MCMC sampling. That gives us posterior samples. And then we can simply train an NLE to give us a surrogate likelihood that we can use in the harmonic mean estimator. So again, avoiding these kind of compounding errors. So these are the three approaches we consider. Here we've applied them to a number of still, fairly toy problems. The first one is a very simple linear Gaussian type model. We have a likelihood available here, so we can actually compare to the ground truth. So on the left, we apply multi-nest, polychord, and also harmonic. And we just make use of the likelihoods, and this kind of gives us a benchmark to compare to. Now, in the likelihood-free setting, we basically don't make use of that knowledge of the likelihood and run the three methods that I just outlined to you in both an amortized and a sequential setting. And we find that we do have, the errors are larger, as one would probably expect, because there's more approximations. But nevertheless, we're doing a reasonable job here of recovering the ground truth. We do find there's some bias in some of these methods, in particular NPE and in RE. Actually, throughout this experiment and other experiments, the neural likelihood estimation approaches appear generally to perform better. And yeah, there's maybe ways we can exploit that further in future. But let me just show you a few examples. So this is a very simple Gaussian one. This is the radiated pine one that we saw previously. Again, for these three different types of methods, both in amortized and sequential, we're recovering a reasonable estimate of the evidence. We also consider a toy black hole merger problem as observed by simulation, a LIGO-like simulation. So now here we want to compare two different models. One of these models was used to generate the mock data, and so we want to see if we can distinguish between these models in this setting. Again, there is a likelihood available, so we can make use of that in this setting, but so that gives us a benchmark to compare to, and we find that we, again, have reasonable estimates for the Bayes factors for all these different scenarios.
Jason, one moment. There is a question from Devarshi.
Yeah.
Devarshi, I tried to switch on your mic.
Yeah, hi. I was just curious what could be the causes behind the NPE and NRE methods being so much more biased, and why we don't see that in the NLE method.
Yeah, I think we need to look into that in further detail, but I suspect with NPE, you actually typically don't sample your training data from the prior, because that would be inefficient, and you instead sample from some kind of some alternative proposal distribution, and then you have to correct for that. And if you, I think, and you essentially, that's what the variance of the NPE models, which I haven't really discussed here, essentially correct for this in different ways. And it depends how well you can correct for that. It's essentially an important sampling type correction. And so I suspect possibly that might be the cause, but we really need to look into it further to know for sure.
Right. Thank you.
Yeah. Okay, so that kind of brings me to the final part of the talk. So far I've been talking about likelihood-based, simulation-based model selection, but in very low dimensional settings. I mean, these are quite recent works, so all of these were toy problems. I don't remember offhand the dimensions, but they're all relatively small. What we really want to do is see if we can also push model selection to very high dimensional settings. And in particular, one area we're particularly interested in is imaging type problems, where now you've got all the pixels in an image. So in order to do that, we've developed a variant of nested sampling, what we call proximal nested sampling, leveraging structure in the problem to allow us to push to very high dimensional settings. So just a quick recap of nested sampling. Again, I'm sure for this audience, maybe people are familiar with nested sampling, so I'll just go through this really quickly, but it'll be necessary to have this content to be able to build our proximal nested sampling on top of this. So very, very quickly, with nested sampling, as maybe many people here know, you essentially want to divide your parameter space into nested subspaces, basically defined by the likelihoods level set or ISO contours. And then you can consider the prior volume within those nested subspaces. And then by a clever reparameterization of the likelihood, you can write the evidence simply as this one-dimensional integral. So you've now moved your evidence calculation to a simple one-dimensional integral instead of a multi-dimensional integral. But you've moved the complexity to how you essentially recover these other components, as we'll see in a second. So essentially for nested sampling, we need to be able to compute these level sets, these isocontours of the likelihood and these prior volumes. So the nested sampling algorithm is essentially you draw these large samples from the prior across the whole prior. So you start with the prior volume of 1, you remove the sample with the smallest likelihood, and then you replace the removed sample with a new sample from the prior, but constrained to be higher than the likelihood of which you just removed. And so then also you need to estimate stochastically the prior volume that is enclosed by the current likelihood level set. And then you simply repeat and draw more and more samples. So this is the nested sampling approach. You need to estimate this enclosed prior volume, but you can do this stochastically. So you can actually estimate the shrinkage ratio of how the volume changes at each step. So if you sample in this manner, you can estimate the prior volumes, no problem. And then given a sequence of decreasing prior volumes, the corresponding likelihoods, then we can calculate the Bayesian evidence just by simple quadrature of that one-dimensional integral. And posterior inferences can also be computed using the importance weights as well. So although nested sampling is designed for computing the model evidence, you can also do parameter estimation as well. So really, the challenge with nested sampling is that we need to sample from the prior, but subject to this likelihood isocontour constraint. So this is really the difficult thing with nested sampling. And this becomes increasingly difficult in higher dimensional settings. So, as I mentioned, we're very interested in particular in inverse imaging problems, where now the pixels are our image of the dimensions of our space, so we're in a very high dimensional setting. But often these types of inverse imaging problems have a lot of structure that can be exploited, and it's very common to consider log convex models in this setting with sparsely type promoting priors, and in many cases, Gaussian data fidelity terms that nevertheless can still include complicated observational effects. But nevertheless, the distribution itself is relatively simple. So what we did was basically try and exploit the structure of this problem, essentially the log convexity of the problem. So these proximal nested sampling techniques that I'm going to tell you about are not completely general. You cannot apply them for any type of distribution. You can only apply them for log convex distributions. But actually, that's very common in imaging type problems. But it's by imposing the structure in the problem that we can then exploit and then push these methods to very high dimensional settings. So just to say, this was work done with Xiaohao Kai, who was a postdoc at UCL working with me, but is now a faculty position at Southampton, Marcelo Pereira, who's a collaborator based in Edinburgh, and Matt Bryce, who's now a postdoc at UCL. Yeah, so I guess the initial work was done by Xiaohao, Marcelo, and myself, and Matt's been getting involved more recently and has written a very nice Python implementation of the Proxnest algorithms, which I'll link to later. So firstly, we have to see how we can pose this constrained sampling problem. We essentially, as I mentioned, consider these log convex settings where both the log prior and the log likelihoods are convex. And then we basically encode the likelihood constraint through indicator functions that, for example, 1 when we're within this likelihood level set and 0 otherwise. So we can then represent the prior distribution that we need to sample from, so the prior with this hard likelihood constraint, simply as follows by including this indicator function, which we can then write in log space as follows, and we basically get one term from the prior and one term which is our likelihood constraint. So now we need to somehow try and sample from this constrained distribution. So for basically exponential type distributions, Langevin sampling techniques can work very well and push to very high dimensional settings. So in the case where the distribution or the log of the distribution is differentiable, we can actually consider this Langevin diffusion process written here to essentially draw samples from an MCMC chain. The problem is we need the distribution to be differentiable. And in the previous setting, our distribution was an indicator function, or not our constraint on the distribution was an indicator function, which is not smooth, is not differentiable. So we cannot directly apply this kind of Langevin dynamics, or Langevin MCMC sampling. But what we can do is regularize the problem. And so we basically essentially leverage ideas from proximal calculus and make what's called a Moreau-Yosida approximation of the constraint. And this essentially regularizes it. It's a smooth regularization of the constraint. So the function itself doesn't need to be smooth, but the Moreau-Yosida approximation is smooth. And in fact, it's differentiable. This is 0.2 here. And in fact, you can express its gradient in terms of what's called a prox operator. And critically, we can also control the approximation well. As this lambda term tends to 0, we recover the original function. So on the right here, I've got a plot of a Moreau-Yosida approximation of the absolute value function. As you increase lambda, so the color here shows the lambda. So as you increase the lambda, you increase the approximation, you make your resulting function smoother.
Jason, you have a few minutes left.
Okay. So with proximal nested sampling, we essentially put these pieces together. So with this constrained sampling formulation, with the Langevin MCMC sampling, and then the Moreau-Yosida approximation of the constraint. And that gives us the following Markov chain, which if we examine in a little more detail, we have this additional term here. And basically, we can understand what this is doing conceptually. If our current sample point is already inside the constraint set, then this term vanishes and we have the usual Langevin MCMC sampling. If we're outside of the constraint set, the prox actually is really a projection onto the boundary of the constraint. And so this term is really a vector pointing in the direction, towards the projection of your current point onto the constraint set. And so this term in the in the Markov chain basically acts to push you back inside the constraint set if you wander outside of it. And so this ensures that generally you're much more likely to come back inside the constraint set and you get much greater efficiency than you would otherwise. So that's really the crux of the advantage of this proximal approach. Yeah, we also have a subsequent Metropolis Hastings set, which actually does guarantee the hard constraint is satisfied. And also just to add that we can also consider non-differentiable priors, which are very common in imaging problems. And we can do the same Moreau-Yosida approximation to regularize those components as well. Yeah, so here I've presented things very generally, but computing these gradients or the resulting prox is actually not trivial, and we need to give some thought to that as well. So we also consider in the paper explicit forms of proximal nested sampling and algorithms for computing these prox operators efficiently. We validated on a Gaussian problem where we can compute the ground truth. We also here applied to standard MC integration, which worked okay in low dimensional settings, but very quickly started to fail. Whereas with the proximal nested sampling, we can push up to dimensions of 10 to the 5 and potentially beyond. And then finally, the last part of my talk is just, again, a toy example showing the application of this, where we're considering a misspecification of a measurement operator. So here we're modeling in a very crude way observations by radio interferometric telescope, where we've misspecified the wavelength of the instrument, and we can see what impact that has on the measurement operator. And we want to use the data to tell us, well, what is the correct specification of this measurement operator? So here's some images of reconstructions where, so M is misspecified. You could maybe guess when gamma is 0.12 that you've misspecified because you have a very poor reconstruction. But if the misspecification is not so large, then you might struggle to be able to know whether you've misspecified the model and which in fact would be the best model. And so we can basically run these different models, compare evidence values to tell us which is the preferred model. And because we're doing simulations, we have the ground truth. We can also just compute the RMS error relative to the ground truth. And indeed, the model evidence favors the model, which is in fact most accurate. And just finally to add, we've recently released a Python code. This was written by Matt Price, implementing these ProxNest algorithms for these imaging problems in particular. And again, it's fairly well tested and extensively documented and available on GitHub if anyone's interested. So that's it. Just to wrap up, many questions we're trying to address in science and in cosmology and astrophysics in particular, questions of model selection. There's been a lot of effort, and model selection, Bayesian model selection is very prevalent in these fields, but there's still, I would say, a number of things still to be done, 3 of which I've spoken about today, these kind of agnostic sampling strategies with the learned harmonic mean estimator, leveraging them for simulation-based inference, proximal methods to scale to high-dimensional settings. And actually, some work we're doing at the moment is also integrating data-driven priors, so learned priors into these frameworks. So thanks very much. I'll finish there.
Thank you very much, Jason, for the very interesting talk. We have a few minutes for questions. Feel free to raise your hand, and I'm gonna switch on your mic. Jeffrey Scargill.
Yes, thanks. Wonderful talk. You briefly mentioned the LIGO black hole gravitational wave thing. Could you say a few more words about that? It looked like you were comparing with and without a merger. Is that what I got from you?
Yeah, so sure, I can jump to that. So basically, we considered 2 models, both with mergers, but different models for the physics of the merger. So I'm certainly no expert in this field, so I'm not really familiar with the underlying physics, but two different models, this spin processing effective one-body numerical relativity simulation and the in-spiral ring-down merger. So it was 2 merger models. We used one of those models in making some simulated mock data. And then the question was, can we compute the evidence to tell us, which is the correct model in this setting? So it's very much a kind of toy problem, but in in a real setting, you might want to run this with data rather than mock data, and then see, which of these 2 models is the best description of this merging black hole interaction. There's very much a toy problem here, but yeah, we're very interested in trying to take this to more realistic setting now for these gravitational wave type problems. In some cases you have the likelihood, but also you're really interested in the GW setting of trying to really accelerate things, so you can very quickly make model selections potentially for gravitational follow-up. So I guess the nominal thing is there an event or not, and then do you want to follow it up? So there's a lot of interest in acceleration as well, where the simulation-based inference can also help a lot. I mean, actually, in other work, we're also looking at variational inference approaches as well to really try and accelerate these things.
Jeffrey, I switched off your mic because there was some noise in the background. Now you can turn on if you... Jeff Scargill. Well, I think it's okay.
Yeah, sorry, I have some noise in the background. So
yeah,
thanks for that answer. I appreciate it.
Someone else? If not, we already had some questions during the talk. We almost reached 1 hour. So.
Yeah, so I would, just to conclude, I guess, say, what I talked about was very recent work. We've applied this to a number of kind of toy problems, which I think, some proof of concept studies where we've, proved that the concept makes sense. But the next step now is really to apply this to more real problems. And actually, we've started doing that, for example, to some GW problems with, I think, kind of 20-dimensional settings and got quite nice preliminary results. So that's the next step, try and, well, also develop out the methodology, but also apply it to practical real problems. And, you know, we put quite a lot of attention to the code as well. So hopefully it's easy for people to use if they're interested. But if anyone does, you know, want to use it and have any questions, feel free to get in touch.
Great. So much work to apply on. So I thank you again, Jason, for the talk. I remind you that the recording of this meeting will be shortly available, and see you next month for the next seminar. Bye, everyone.
Thanks.